Hello, everyone. This is Hooman. The study is trying to find a new traffic capacity flow for the highway bridges. And that study has been conducted in Washington State University under supervision of Dr. Lee. Before starting, let's get started with some kind of the facts about the problem statement. As you know, the bridges are very important and vital structural components in the transportation networks. If there is a kind of the damage goes to the structures, by falling the bridges, there is a possibility of the failure to the networks. And that's why we need to determine what is the remaining load carrying capacity or what is the traffic load carrying capacity after disaster. So therefore, the main question here is to find out the relationship between the traffic flow and the structural failure. In this study, we are trying to follow three main goals. The first goal is that to determine some kind of the new damage index. We already used the fragility curves. However, here we are trying to use introduce a new type of the reliability intensity surface to determine the damage condition of the structure during or after disaster. Then using that kind of the reliability intensity surface, we can determine the new kind of the relationship between the load carrying capacity and the remaining traffic flow capacity of the bridges. And also by consideration of the probabilistic seismic hazard analysis, we can determine a new type of the resilience metric to measure the capacity of the networks. That flowchart is trying to illustrate what is the procedure to get that kind of the index, or that kind of the safety index. First, we need to consider some kind of a set of the scenarios. After that, we need to figure out what is the seismic hazard curve. We can take that seismic hazard curve from the USGS or other website, or we can create that kind of the seismic hazard curve by own. After that, as you know, the seismic event is a kind of uncertain event. We need to determine the mean and standard deviation of that earthquake event to measure the intensity measure. With consideration of the probability aspect of the earthquakes, we can find some kind of a joint distribution function between the probability of the happening of the earthquake and with consideration of the mean and coefficient of variation of the earthquakes. Then we can generate that kind of the reliability intensity surface to make sure what is the remaining load carrying capacity of the system. With consideration of the relationship between that reliability index and flow capacity, we can determine what is the expected post-earthquake traffic flow. So why here we are focusing on the reliability intensity surface and what is the advantage of that reliability intensity surface, which could be considered as a new toolbox for identifying and quantifying the damage of the system. With comparison of our conventional methods or traditional methods, which is the fragility curves. There are some shortcomings refers to the fragility curves. The first one is the consideration of the distribution of the fragility curves based on the fundamental idea of the fragility curve. The fragility curves idea relies on the normal distribution. That means the failure probability of any events using the fragility curve should be behaves as a log normals, but the fact is not true. Some kind of the resistance or loads distribution not following the log normal distribution, and as a result, your failure probability distribution is not log normal distribution forever. So that's why we need to consider the real probability distribution function for the failure. The other fact we are using the reliability intensity surface is that some kind of the events like earthquakes have various type of the uncertainties. We need to consider both ultra-re and epistemic uncertainty in consideration. And the other facts of using the reliability intensity surface, we have some kind of the understanding about the sensitivity analysis between the load and the load structural carrying capacity or resistance. So, the idea of the finding the load carrying capacity or determining the reliability index of the system is established based on the limited state function. On the left side, you will see the very basic expression of the limited state function, which is just the differences between the resistance or load carrying capacity minus the resistance. Both R and Q stands as a distribution. If you take that distributions to consideration and put them into the limited state function, you can find the failure zone. Those solid lines on the left side top figure refers to either the distribution of the load or distribution of the system. So here in this research, we just try to develop a new kind of the idea to capture the reliability index by just modifying the limited state function a little bit. So previously, in order to find the reliability index of the system after disaster, let's just take a look at the top left side figure. That dashed blue line refers to the distribution of the resistance before disaster. That's why it's called as an intact system. So by applying their forces or happening the extreme events, we're expecting the load carrying capacity will be decreased, and as a result, your resistance will be shifted to the left side to get the more failure. So in order to find the reliability index of the system after disaster, it means you need to using the finite element analysis, apply all damage, consider the cracks, have some kind of the prediction about the failure and so on, and take them all to consideration and try to get that distribution after damage, that blue solid line. And then by having the same constant loading scenario, you can find the probability of the failure. But that idea can be developed just using the variation of the load. We can assume the load, the resistance is constant, but you can make a change to the distribution of the load. By increasing the intensity of the load, you can just shift the load distribution to the right side. And as a result, the probability of the failure of both illustration on top and bottom could be the same. And we can develop the reliability in the surface for any single elements of the bridges, and using the system reliability, we can find what is the reliability intensity surface for bridges. As I mentioned, the main advantage of that, the reliability intensity surface refers to the coefficient variation axis of that illustration. For example, if we don't have enough information about the possibility of the intensity of the earthquake, we can take that to the coefficient of variation into consideration and find the reliability index of the system after disaster. So the second step, we need to make a relationship between the load factors or load carrying capacity and the reliability index. For example, based on the design practice of the H2LRFD, the top in the table on the left, in the right, sorry, at the middle column, we got the equations which comes from the load combination from the H2LRFD. Let's assume that the governing loading combination refers to the combination of the dead load, wearing dead load, and the live load with consideration of the impact factor. So if you take that to consideration and apply the reliability index, the reliability index for the pier or column of the bridge is going to be 4. If you apply just a third quarter of the live load, the required reliability index to withstand against the applied traffic load, which is 0.25 reduction factor to the very initial consideration of the load, is going to be 3.15 and so on. It means by reducing the live load, the structure needs lower or smaller amount of the reliability index. If you increase the loads, the reliability index should be increased. That's the philosophy of the reliability-based design procedure. So therefore, we can make a relationship between the live load and the required reliability index. As I mentioned, for the fully load carrying capacity, you need to consider the reliability is about 4 to bring enough stiffness and safety to the bridge. The next step is that to quantify what is the expected flow capacity for the bridge. So that probabilistic illustration and expression help us to determine the expected value. In that equation, the P SI refers to probability of the seismic events, and the rest of the probability distribution refers to the conditional probability with concentration. For example, the F sub IM COV refers to the probability of the intensity of the earthquake with concentration of the given scenario. Also, the middle part is the probability, the distribution of the reliability index with that given COV intensity measure and so on. And accordingly, we can find what is the flow capacity of that bridge with respect to that given extreme event. In order to make that idea clear, let's take a look at the illustrative example. In that illustrative example, let's assume we got a network between the city A to city B. We have a different type of the bridges with 3, 4 piers or so on, which has a different reliability index. And it was assumed that the B1, which is the bridge 1, it was located at the given location on the table. This is very, very imaginable kind of the example. So for each kind of the location, we have information about the return period of the earthquake with the corresponding the intensity measure. The intensity measure considered for this paper, for this research, was peak ground acceleration. So we can derive the seismic hazard curve for that given bridges. For example, for bridge number 1, bridge number 2 and 3 and 4, we have a different type of the curves which can be taken from the USGS website. And also you can take the uncertainty of the PGA of any kind of the earthquakes event to consideration. For example, for this study, we are assuming that the distribution of the uncertainty of the earthquakes behaves as a extreme type 2 distribution with a COV of the 0.2. So for each different location, you can get the various type of the probability of the happening with consideration different type of the return time period. So accordingly, you can find what is the reliability intensity surface for piers, girders, and band cap. We have assumed that those kind of the bridges for those locations are the highway bridges, which has 3 main structural components: girders, band cap, and the piers. The piers could be treated as a parallel system. Girders are going to be also parallel system. And the band cap, this is just one single element. And all elements could be considered as a series system. So using the system reliability, you can eventually find what is the reliability intensity surface for bridges. That mesh, blue mesh type on the bottom for the bottom figures refers to the reliability intensity surface for the bridge after disaster. And that kind of the colorful surface on top refers to the reliability intensity surface for bridge before disaster. For example, that kind of the one axis refers to the number of the piers, the other axis refers to the correlation between the elements. So by having the number of the piers and different correlation, you can find what is the reliability index of the bridge before and after disaster. And using the system reliability, approach, you can derive what is the reliability intensive surface for entire of the bridge after or even before disaster. So then we can use that proposed equation to determine what is the expected flow capacity for various locations. And accordingly, we can find what is the expected flow capacity for that given earthquake scenario. For the first link, which is the connection between point A to that the merge location, we can find the expected flow capacity using that following equations, and therefore for entire of the link between point A to the point B, that 0.9 or 90% is going to be the expected traffic flow for that given network subjected to the given loading scenario. And based on the Monte Carlo simulation and some kind of the other simulation approach, we can propose the load carrying capacity or remaining allowable traffic flow capacity based on the expected flow capacity with that given airspeed condition. For example, if the expected value comes from the probabilistic equation is equal to the 1, after disaster, you can claim your bridge system, your transportation system, have a complete load carrying capacity, traffic flow. If that expected value fall between the 0.75 and 1, the allowable traffic flow after disaster is just third quarter of what was the traffic flow before the disaster, and so on. For example, if the expected traffic flow with that given condition is less than a quarter, you may put a sign after disaster, and you will not use that bridge because there's a high possibility of the failure. So as a conclusion, that study proposed a new reliability intensive surface, which is a powerful probabilistic approach to determine what is the remaining structural safety or what is the remaining or condition of the structure after disaster, which could be used as an alternative of the fragility curves. Accordingly, we introduced the reliability-based indicator, and using some kind of probabilistic approach to determine what is the expected traffic flow, and followingly, we just propose what is going to be the recommended value of the expected traffic flow with respect to the load factors. So thank you for attention. If there is a question, please shoot your question.